Okay, so today we have the USACO 2019 US Open contest goal problem number 2 of I would walk 500 miles. So you can pause the video first and look at the problem statement yourself. Okay, I suppose you read the problem. So basically, what the problem is asking for is Farmer John has N cows, and the N cows are to be divided into K non-empty groups. And right now, each cow have to walk a certain distance to see another cow, given by the formula of this. And he's trying to maximize the minimum value any cow has to walk to see any other cow in a different group as itself. So you can pause the video again and think about it yourself. Okay, I suppose you thought about it. So what's the first thing that we notice when we see this problem? Well, obviously, we're trying to maximize the minimum value, right? What does that sound like? Obviously, binary search. And we can try using binary search to solve this problem. And however, the time complexity would be incorrect. So here's the pseudocode. If we try binary searching the minimum length of all edges that run between components, we can then iterate through all of the n squared edges. And if any edge has its length of less than mid, which means we have to get the two endpoints to be in the same component. We use the disjoint set to maintain the components, and then the number of group has to decrease because we just combine two groups. And if at the end we see the number of group is less than k, that means this mid doesn't work, right? That means this minimum side length is too big. So then we have to go down. Oh no, we have to go down. No, this minimum side length is too small and we have to go up. Otherwise, we have to go down. But however, this code has an incorrect time complexity because as you can see, the binary search is log 1e9 because we know binary search has time complexity of log and the range is 10 to the 9th power. It's actually 2 times 10 to the 9th power. And then we have iterating through each of the n edges, which will give us n squared complexity. And then we have log of n squared because we need to use the disjoint set, which will give us another log of n squared. And this will be way over the time limit as n is 10 to the 7,500. So binary search doesn't work. Well, what else can we do? Well, instead of binary searching, actually, we can think about the problem in another way. Instead of trying to maintain which edge we need to get rid of and which edge we have to get in the same component, why don't we just look at it in another way of just constructing k connected components? We're basically trying to get the k smallest edges and construct k connected components. And then the k plus 1 smallest edge that run between connected components is going to be our answer, right? And what does this sound like to us? Well, that sounds like Kruskal, doesn't it? The minimum spanning tree algorithm of Kruskal. And I did indeed write a program for this, and this time it's not even pseudocode because I tried this method. And so basically what we're trying to do is we just do a regular Kruskal algorithm, which is right here. I used, this is not like classic Kruskal because I used the priority queue, but the main idea is the same. And if you know how the Kruskal minimum spanning tree algorithm works, you should be able to understand what I'm trying to do here. And basically what I'm doing is once the number of connected components is less than k, that means we hit the k plus 1's smallest edge that run between components, and then that's the answer, and we print the answer. However, this program will still have an incorrect time complexity because we have to sort all the edges, and there's n squared edge, and we know sorting have time complexity of n log n, and since we have n squared edges, the complexity is n squared log n squared, and since n is 7,500, that will be incorrect. However, you can receive 65% credit using this algorithm. And now comes the fun part of this problem. We already know how to construct the k smallest components, but that will have an incorrect time complexity. But what if, instead of constructing k, what if we connect all of them, meaning we make a minimum spanning tree and then we remove k minus 1 edges? Because think about it, we already have a lot of algorithms that can give us a minimum spanning tree in n squared time. We just have to remove the k minus 1 biggest edges, the k minus 1 longest edges within this minimum spanning tree. So with this idea, we can write a third code. In this case, the code using the prim algorithm. So the prim algorithm, this is a code for a regular prim algorithm in which we use a priority queue to maintain the edge. It's actually a lot like Kruskal. On Dijkstra. If you know what Dijkstra's shortest path algorithm is, you should be able to implement prim pretty easily because they both use a priority queue and they both maintain two sets, one of which is already visited and one of which is unvisited. And then every time they find the shortest edge that connects a visited and unvisited point, and then use that edge to add the unvisited point into the visited set. So you can just look up Prim's algorithm, and it's actually really similar to Dijkstra. And for this problem, instead of using the regular Prim algorithm in which we use a priority queue and push each edge into a queue once, giving us the E log E time complexity, instead of using a priority queue, we can just go over each of the endpoints while maintaining an array D, which represents this point which is not in the minimum spanning tree yet. It's minimum distance between this point and any points that's already in the tree. So basically, every time we iterate through all of the endpoints, and if this point is not yet in the tree, we find the minimum point that's not yet in the tree. We find the minimum distance between this point and the point in the tree, and then we add this point into the tree. Then we renew all of these. So it's basically like Prim, except with slight modification. So now the complexity, instead of E log E, we have n squared, right? Because it takes n complexity to add the n edges. And each time we add an edge, we have to iterate through all the endpoints to find the point that's not in the MST, that's closest to the MST. And now, each time we add a point, there's a distance between this point and is distant to any point on the tree. So we add that edge onto this E array. And then finally, we sort the array in descending order. And then the k minus 1th biggest edge is going to be the edge. It's going to be the smallest edge that we have to remove from this tree in order to have it have only k connected components. And this is the edge with the minimum value between two cows that are in different components. This code, along with the solution that I wrote above, is going to be posted in the comments if you want to check it out. So now we can come back to our question today, and hopefully after this video, you will understand how exactly to solve this USACO 2019 US Open problem number 2 of I will walk 500 miles. Thank you for watching.